And hi everyone, this is Yiming from Lehigh University, and together with my teammate Wai Qian and my advisor Professor Yu, our presented topic is asymptotically compatible Meshfree quadrature rule for non-local problems. So in this report, I will introduce a Meshfree scheme for compatibly non-local integral equations. That Meshfree means that it can eliminate the complex geometric computation as shown in these literatures, and we'll use our numerical scheme to develop a mesh discretization of the non-local models, such as the non-local diffusion and the bound-based peridynamics, to be specific in this report. And our code is written in C++, which we treat general Meshfree schemes with tools for non-local problems. And at last, we will apply our method to realistic mechanical engineering problem. To begin with, I will briefly introduce the notation. So we are generally interested in the general non-local IDE of the following form. The K here is the radial kernel centered with fixed x, and which is supported on a ball with radius delta and centered at point x. For the well-posedness of this kind of problem, we need the definition of the volumetric non-local boundary, and it is the color of thickness delta around the classical boundary partial omega. Omega is our computational domain, and they are denoted as like this respectively. The union of those two parts will be denoted as omega delta. Our Meshfree quadrature rule defines a collection of quadrature points, SQ. The SQ here doesn't have to be uniform. It can be with a uniform mesh with some disturb, or you randomly pick a point inside the horizons. We seek for the quadrature weights of the integral supported on the ball of the following form, which is inspired from the classical Gauss quadrature rule. And the weights can be obtained by solving the optimization problem. So we want to minimize the summation of the square of the weights with the constraint. In the constraint, the IP here denotes the quadrature functional of the function p, and which is the left-hand side of this formulation, but replace f with p. And IHP here is corresponding discretized approximation, i.e. the right-hand side of this formulation, but change f to p. The function space VHP come from is a finite dimensional space, which we want to exactly reproduce. And we define VH as the union of two sets, the PM, i.e. the polynomial basis up to order m, and SKNX, which is the product of the kernel function and the polynomial basis. To solve the optimization problem, we apply the Lagrange multiplier method, and it can be transformed into this saddle point problem. I is the identity matrix, omega are the quadrature weights, lambda are the Lagrange multipliers, and B here consists of the reproducing set we evaluated at each quadrature point. And the G here consists of the corresponding integral of each function in the reproducing sets over the ball. By eliminating the Lagrange multipliers, this linear system can be solved. The omega can be solved using this formulation, and X is the short complement. With the quadrature weights in hand, we can write down the discretization of the non-local problems. For a static case, it looks like this, and Kij is the function value evaluated at point xi and xj. For dynamic cases, adapt the implicit time discretization to the second derivative of the time, and the formulation will be looking like this. And since here we have the time is a time-dependent problem, the solution UIN here is the value of the function value at point xi and time step tn. The convergence theorem for our method for the truncation error and solution error can be found in our works before. Due to time limitation, I will just show the numerical verification and the result of the solution of the convergence solution. So this static pseudocode describes the procedure of the general procedure of our codes. First, an initialization to the configuration xi, which is in the set denoted as set of capital XH, and this is a subset of the whole domain omega delta. And for each point xi, we need to find the neighborhood xi for each point. In the one-step pre-processing function here, firstly, in the iteration for each point in this capital XH, we need to generate the quadrature weight omega I according to the optimization problems and for all the points inside the neighborhood. And then we're going to build the stiffness matrix. If xi is inside this omega, then we will build the stiffness matrix and the corresponding right-hand side using the discretized version of the non-local equation. And else if it is in the non-local boundary, then we will just simply set the Dirichlet boundary condition to it. And then we can solve the linear system. You can use any linear solver to get a solution of this. And the UH delta here denotes the numerical solution. And then the post-processing. So far we have a review of the Meshfree method, and now we can ready to apply the method to some specific models. The first one is called the non-local diffusion model, which is described in the following literature, and it can be written out in this form. This is a non-local companion of this local diffusion equation. In this example, we'll test the asymptotic compatibility of our numerical method for the non-local diffusion problem. The analytical solution is built using a triangular function, and the computational domain is 2D here. That's the Cartesian product of the interval from 0 to 1. To test the asymptotic compatibility, we will set a fixed ratio of the horizon delta and the mesh size h. And this example, we use 3.5. And then we let delta and h goes to 0 simultaneously, and measure the L2 error and the L-infinite error between the numerical solution and the analytical solution. We found that both of them shows a second-order convergence to the local limit. Next example is the bound-based peridynamics. The question we adapt here is bound-based peridynamic solid models, specifically the linearized microelastic brittle model described in literature 8 to 9. And the problem is of this form, the coefficient C here is different for the different, varies with different dimensions. And chi here is the bulk modulus. For this case, we also do a numerical verification, and the analytical solution looks like this with its also a triangular function. Computational domain is again 2D, but the interval is from -pi to +pi. The left figure shows the convergence of the truncation error. And again, we fix the ratio of delta and h as 3.5 here. And truncation error here shows the second order convergence to the local limits. And in the figure on the right-hand side, the first thing we can observe is the second order convergence of the solution error to the non-local limit. And along with this result represents the convergence result of the standard peridynamic quadrature. Actually, we use the PD lamps here, and we have found that compared with the Meshfree method, the convergence of the traditional method is a little bit slower. In a damage modeling, the fracture is modeled by breaking the bonds. The quadrature rule can be modified very straightforward. So if the bound is unbroken, it will remain the same. But if the bound is broken, it will be simply set to 0. And then we can define the string of the bond as follows, which can be able to compute it using the solutions. The bonds will be broken in two circumstances. The first is that a pre-process of the initial crack of the problem, or at each time step, if any bond is exceeding a critical stress value, then we will break the bond. Now, this pseudocode describes the procedure of the dynamic case. Again, we have the initialization, but now the pre-processing is it's just for generate quadrature weights, since the weights doesn't have to be generated again at each time step. And for the main iteration, this is a time iteration, and at each time step, we're gonna build a stiffness matrix and right-hand side and use any linear solver to get this solution. For this build stiffness and matrix and right-hand side function, first thing we're gonna do is to initialize the crack and update the boundary condition. So if it's in the first time step, we just initialize the crack and use the boundary condition at the first time step. But if it is not, it is the time step after that, we will examine the boundary breaking criterion using the solution that we get from the last time step, and then the boundary condition will also be updated using that result. And then we go to the same procedure as build a stiffness matrix and right-hand side. So with a set of solution, you can do the post-processing to compute the error or plot or crack or anything else. And we do a numerical validation of the KW experiment from literature 10. And thanks for Pablo for the detailed describe of this experiment before. So I will just go through the numerical part of our experiment. We applied the homogeneous dirichlet boundary condition U00 on the top of the plate to the left and the right-hand side of the notches. And the impact is modeled by imposing a fixed displacement of U equal to 0, negative 22t, since at each time step between the two notches. And for the remaining sections, the boundary at the sides and the bottom will be treated as the free surface, and i.e. breaking any bonds that cross the omega and the partial omega delta. And this video shows the simulation of a numerical method to the KW experiments. So as time goes by, we can observe this famous crack at 68 angle degree. In this figure, we tried different refine of the mesh. So from left to the right-hand side, it's using the mesh size of 1/64, 1/128, and 1/256. And all of them shows a consistent crack pattern. And all of them, we can observe this 68 angle crack in all of the cases. So to recap, we introduced an asymptotically compatible optimization-based Meshfree quadrature rule for general non-local problems. And the optimal convergence is second order to local limit for the case without fracture. And high order convergence can be achieved to non-local limit if you use very high order polynomial basis. The numerical verification of the convergence to local theory is shown here. We have first order and second order for the model with and without fracture respectively. The numerical validation successfully reproduced the KW experiments. And at last, we provide software tools with application to some example of the non-local models. The implementation can be found in this GitHub link. It is written in language C++. The example shows are non-local diffusion, bound-based peridynamics, and KW experiments showed in this presentation. And here's the brief review of the branch. And I'd like to thank all the collaborators contributed to this work, and a huge thanks to the NSF awards. If you want to cite this work or for more detailed convergence theorem or the numerical test, please find more in the following references. Okay, thanks again for listening.